The first imbalance appears a fundamental paradox. The early universe, just after the Big Bang, was not chaotic in the way we might expect. It was remarkably smooth, almost uniform in temperature and density. From a thermodynamic perspective, this was an extraordinarily low entropy condition. Why would the universe begin in such an unlikely configuration? If entropy always increases, then the starting point must have been exceptionally ordered. But physics offers no clear reason for this initial condition. It is not explained by known laws. It is simply assumed. And so, the direction of entropy may not be a consequence of the universe's laws, but of its beginning. A beginning we do not yet understand. A direction without a cause. Time, as we experience it, flows in one direction. We remember the past, not the future. We see broken cups, not spontaneously reassembled ones. This asymmetry is deeply tied to entropy. Yet the fundamental laws of physics, those governing particles and forces, do not prefer a direction of time. They work just as well forward as backward. So why does entropy increase only in one direction? This question reveals a deeper inconsistency. If the laws themselves are symmetric, then the arrow of time must emerge from something else, something outside the equations. Perhaps from initial conditions, or perhaps from our perspective within the system. But if the arrow of time is not fundamental, then entropy's increase may not be fundamental either. It may be a consequence of how we observe the universe, rather than how the universe truly is. The paradox of structure. Despite entropy's relentless push toward disorder, the universe is full of structure. Stars form from diffuse gas. Galaxies organize into vast cosmic webs. On at least one planet, chemistry becomes biology, and biology becomes consciousness. At first glance, this seemes to contradict the second law of thermodynamics. But the usual explanation is that local decreases in entropy are allowed, as long as the total entropy of the universe increases. A star can form because it releases heat into its surroundings. Life can emerge because it consumes energy and increases entropy elsewhere. This explanation works mathematically, but it raises a deeper question. Why does the universe permit such complexity at all? Why do the laws allow for temporary pockets of increasing order, even as the overall trend moves toward disorder? It is as if the universe is not simply decaying, but exploring, a dynamic system balancing between chaos and structure. And that balance is not fully understood. The black hole exception. Black holes introduce a strange twist to the story of entropy. When matter falls into a black hole, it seems to disappear. Information about its structure, its arrangement, its history, all of it becomes inaccessible. This appears to violate a fundamental principle that information cannot be destroyed. To resolve this, physicists assign entropy to black holes. In fact, black holes have the highest entropy of any known objects. Their entropy is proportional not to their volume, but to the area of their event horizon. This suggests something extraordinary, that the information content of a region of space might be encoded on its boundary. That the universe itself could be described in fewer dimensions than it appears. And if that is true, then entropy may not just measure disorder, it may reflect a deeper, hidden structure of reality. The heat-death horizon. If entropy always increases, then the universe has an endpoint, a state of maximum entropy, where all energy is evenly distributed. No gradients, no flows, no processes, no stars, no life, no change. This is often called the heat death of the universe. It is a future of perfect uniformity.
But there is something unsettling about this conclusion. Because if the universe is moving toward this state, then we exist in a very special moment, far from equilibrium, rich in structure. Why now? Why does the universe appear to be in a transient phase where complexity is possible? Some suggest this is a selection effect. We observe this moment because it is the only one in which observers can exist. But others wonder whether the trajectory toward heat death is as inevitable as it seems. Could there be mechanisms we do not yet understand? Cycles, fluctuations, or hidden processes that prevent the universe from reaching equilibrium?
Fluctuations in the void? In a universe approaching maximum entropy, something curious can still happen. Random fluctuations. Even in near-perfect equilibrium, statistical mechanics allows for rare, spontaneous decreases in entropy. Given enough time, these fluctuations can produce localized pockets of order. In theory, an entire galaxy, or even a conscious observer, could arise from such a fluctuation. This leads to a strange implication. If the universe is old enough and entropy has had enough time to increase, then most observers should be products of random fluctuations, not the result of cosmic evolution. These hypothetical observers are sometimes called Boltzmann brains. Yet we do not experience ourselves as random, isolated consciousnesses appearing briefly in chaos. We observe a structured universe with consistent laws and a coherent history. This discrepancy suggests that our understanding of entropy, time, or probability may be incomplete.
Quantum uncertainty and entropy? At the quantum level, the concept of entropy becomes more subtle. Quantum systems can exist in superpositions, states that are not simply ordered or disordered, but something in between. When a quantum system interacts with its environment, it undergoes decoherence, appearing to settle into a definite state. This process increases entropy. But the underlying quantum evolution is reversible. This creates a tension. If the fundamental processes are reversible, then where does irreversible entropy come from? Some interpretations suggest that entropy is not a physical property, but a measure of our knowledge, our inability to track every detail of a system. If so, then entropy's increase may reflect a limitation of observers, not a fundamental feature of reality. The cosmological constant puzzle. The expansion of the universe adds another layer to the mystery. Driven by what we call dark energy, space itself is stretching, accelerating over time. As the universe expands, matter becomes more dilute and entropy increases. But the presence of dark energy suggests that the universe may approach a de Sitter state, a kind of equilibrium with a finite entropy. This introduces a paradox. If the universe has a maximum entropy, then how can entropy continue to increase indefinitely? And if it cannot, then what happens when that limit is reached? Does time lose its meaning? Does change cease entirely? Or does something beyond our current models intervene? Information and reality. Entropy is deeply connected to information. In many formulations, entropy measures the number of possible microstates corresponding to a given macrostate, the amount of hidden information. This connection has led some to propose that the universe is fundamentally informational, that reality itself may be a kind of computation. In such a framework, the increase of entropy could be seen as a loss of accessible information, or perhaps a transformation of information into less structured forms.
But if information is truly fundamental, then it should not be lost. This tension between entropy and information conservation remains unresolved. It hints that our current understanding may be incomplete, that entropy is not just about disorder, but about how reality encodes and processes information.